friends, in this lecture, we talk about Drude model and failure of classical theory. First, let us revise the plan of the course. We would like to understand electronic properties of metals, semiconductors, and insulators. Metals can be understood to some extent by using free and independent electron gas model. Free electron model ignores electron-ion interaction and independent electron model ignores electron-electron interaction. Free and independent electrons can be discussed at two different levels: classical and quantum. In this lecture, we shall focus on classical free electron gas model proposed by Drude around 1900, before the development of the quantum mechanics. Drude applied kinetic theory of gases to a metal considered to be a gas of electrons. First, let us understand how does the electron gas form. Let us consider sodium. Sodium has 11 electrons. The electronic configuration is 1s2, 2s2, 2p6, 3s1. A metal is formed when approximately 10 power 23 atoms come together. So this is the Avogadro's number. In a metal, the nucleus and the core electrons retains their free electron configuration. So I have a nucleus shown here, and then I have core electrons, 10 of them, occupying this region. So this is the case of a single atom. When a single atom comes together and forms the solid, then what happens is the nucleus and the core electron, they roughly retain their atomic configuration. Nucleus and core electrons, they together form the positive ions. Okay. And these positive ions, they are very heavy and immobile than compared to the single electron. The valence electrons, which is 3s1 in case of sodium, gets detached and moves freely, forming the electron gas. Let us understand the assumptions of the Drude model. It is assumed that the Coulomb interaction is absent. That means there is no electron-electron interaction and there is no electron-ion interaction. The first one is known as the independent electron approximation, and the second one is known as the free electron approximation. Although electrons are not experiencing any force due to the ions and due to other electrons, however, electrons feel force due to the external fields like electric or magnetic field. Next, electrons are scattered by some mechanism. Drude assumed the mechanism to be electron-ion collision, and electron-electron collisions are ignored. Probability per unit time of electron-ion collision is 1 over tau, where tau is the relaxation time. Note that free electron density is 1000 times higher than the classical gas at room temperature. Despite this, and despite strong electron-ion and electron-electron interaction, Drude very boldly applied kinetic theory of dilute gas to the gas of electrons. Let us try to understand what happens between two collisions. In the absence of any external electric field or magnetic field, electrons move in a straight line until the next collision, taking place approximately every tau second. If external field is applied, motion of electron is determined by the Newton's second law of motion. Let us try to understand this using a schematic diagram. In this diagram, the gray arrows are showing all the possible directions in which the electrons can be scattered after a collision. Black arrows are showing the actual direction along which the electrons are getting scattered. Clearly, if there is no external field, the electrons will get scattered randomly, leading to zero current. However, if there is some external field, for example, electric field in this direction, then the electrons are experiencing some force in this direction. In this case, the electrons move according to the force acting on them, despite scattering in random directions. For example, you see electrons are still getting scattered in random directions. In this case, it is getting scattered in this direction. However, since there is some force in this direction, it will initially start moving in this direction and then gradually it will turn around. Similarly, in this case, it will start moving in this direction initially after the collision, but gradually it will turn around. As a result of this coordinated motion, we expect to see some current in this case. Let us define average total momentum per electron as P of T. This is the vector sum of momentum of all the electrons present in the system. So that means I sum over all the electrons present in the system and then divide it by number of electrons present in the system and define that as P of T. Note that in the absence of field, PIs, they are completely random, and as a result, P of T is equals to 0 and there is no current. Now, in the presence of the applied field, we can write the Newton's second law of motion as dp dt, rate of change of momentum, is equals to force, and then there is some additional term. Okay, this is like the damping term. Okay, now let us try to understand why do we need the damping term. Note that the damping term arises from the electron-ion collision. Now let us consider that if we do not have the damping term, what would happen? In this case, the equation just turns out to be dp by dt is equals to F. There is no damping term. Okay, and the solution is P of T is equals to force times time. So in this case, what happens? The momentum keeps increasing like this along this dashed line. And once the field is switched off, electrons keep moving. So at this point, we switch off the field and then the electrons keep moving with constant momentum. However, this clearly contradicts with what we know from our experience. We know that current does not keep increasing with time like this as we apply an electric field. Moreover, once the electric field is switched off, the current becomes zero instead of maintaining some constant value. Let us see whether the damping term helps us to remove the inconsistency. With damping, the solution of this equation looks like this. So now you see in this equation, as T increases, this term becomes insignificant. Thus, momentum and current does not keep increasing with time, but saturates to some constant value, ED is equals to F times tau. This you can see here. Moreover, once the field is switched off at this point, the momentum as well as current becomes 0. So let's see that how does that happen. So dp dt is equals to minus p by tau after I switch off the field. And then you can solve this. P of t is equals to pd e power minus t by tau. And as time increases, the current becomes 0 exponentially. Finally, we can ask the question that how long does it take for the current to saturate? So you see the current will reach the saturation level at this point, and after you switch off the field, it will move to 0 in this fashion. The question is how long does it take to reach the saturation level, or once after you switch off the field, how long does it take to become 0? The answer is very small time, because tau is of the order of 10 power minus 14 second. Thus, the saturation should take less than even a nanosecond. Remember that tau originates from the electron-ion collisions, and it helps to maintain the steady state. That is, what do we mean by steady state? dp dt equal to 0. The rate of change of momentum is 0. So it helps to maintain the steady state both in the presence or absence of the electric field. Let us now discuss DC electrical conductivity. We know that if we apply some electric field, this is the force on the electrons, where Q is the charge of the electron. Momentum in steady state is given by force times tau, where tau is the relaxation time. Now we can define current density. J is equals to NQ times V. For example, if the wire looks like this, and then this is the V velocity, and then we can define current density J as this, where N is the carrier density and Q is the charge of the electron. And ultimately, using this equation, we can get J in this form. We can write the microscopic forms of Ohm's law like this. J is equals to sigma times E, where sigma is the conductivity. The derivation is very simple and given here. So comparing these two equations, what we can say is that sigma, the electrical conductivity, is equal to N Q squared tau by M. So in this equation, N, the carrier density, it can be estimated. Q is a fundamental constant because this is the charge of the electron. M is the mass of the electron, another fundamental constant. The only term that remains here, which is very difficult to predict, is tau, because tau will depend on temperature, tau will depend on purity of sample, etc. Drude model will be put to test in different experiments. However, we shall always look to have quantities independent of tau, because tau is not so easy to predict. Hall effect is one of the experiments which we are going to use to test the Drude model. In this experiment, we apply an electric field in the positive x direction and a magnetic field in the positive z direction. In the absence of the magnetic field, electrons would move in a straight line shown by this dotted line. However, because of the magnetic field, electrons feel a force in this direction shown by the blue arrow. So in presence of both electric and magnetic field, the electrons will feel of force, which is known as the Lorenz force. And the movement along the blue line will happen because of the magnetic part of the Lorenz force. So as a result, positive and negative charges will build up. So electrons are experiencing a force in this direction. They will move in this direction, and the negative charge will build up along this end, and a positive charge will build up along this end. As a result, some electric field will build up along this. Now, this electric field is going to oppose the motion of the electrons that was happening due to the magnetic field. In steady state, the forces are going to balance out each other. We can experimentally measure something called a Hall voltage, V of H. Now, we can define a term called the Hall coefficient, which can be calculated from the experimentally measured value of Hall voltage, I of X, the current in the X direction, and B of Z, the field applied in the Z direction. In the next slide, we shall find that Drude model predicts RH is equals to minus 1 by NEC. Thus, if we can measure RH from the experiment, which we definitely can do, we can calculate the charge carrier density N is equals to minus 1 by RH EC. Because E and C, these are two fundamental constants, charge of electron and speed of light, and RH we have measured from the experiment. Thus, we can calculate the value of N, and I note it as N of O. Now, we can easily estimate the charge carrier density N from the crystal structure data. So what we are going to do is that we will see that what are the values of N0 or NO we get from the experiment, and what are the values we calculate from crystal structure data, and we will try to compare them. But before that, let us derive this term from Drude model. This is the equation of motion. dp dt, rate of change of momentum, is equal to, this is the Lorenz force part, and this is the damping term. In steady state, dp dt goes to 0. So now, then the equation can be written as P by tau is equals to Q E plus 1 by C V cross P. Q is the charge of the electron, tau is the relaxation time, this is the electric field, V is the velocity, B is the magnetic field, and C is the speed of light. Now, let us write this equation term by term. So, let us write the x component. So, this is Px by tau is equals to Q Ex plus Q by C Vy Vz. This term you can easily get by calculating cross product. So, this is I J K Vx Vy Vz Bx Vy Bz. And if we write the x component, so this turns out to be Vy Bz minus Vz Vy. But we know that the magnetic field is only in the z direction. That means y component of the magnetic field is 0. So this term is 0, and that leads to this equation. Now, if we take this equation and multiply both the sides by NQ by M. So thus we have NQ by M, Px by tau is equals to NQ square by M Ex plus NQ by M, Q by MC, Py, Bz. Okay. And then you see that this is like NQ Px by M. That turns out to be G of X. And then tau is brought to this side. So that is NQ square tau by M E of X plus these terms, we can just combine them like this: Q times Bz divided by M times C tau Jy. So now if we just write Q Bz by MC as omega of C, then what equation do we have? And then you note that this is equal to sigma naught and this is equal to omega C. So if we note that, then we can just write this equation as Jx is equals to sigma naught times Ex plus omega C tau times Jy. Similarly, we can write the y component and get this equation. Jy is equals to sigma naught Ey minus omega C tau Jx. Now we have two equations, this and two unknowns, Jx and Jy. If we solve the two equations, then these are the values of Jx and Jy. Now, in steady state, we know that there is no current in this direction. The current is only in the x direction. So that means in steady state, Jy is equals to 0. So if we put Jy equal to 0 in this equation, then we get Ey is equals to omega C tau Ex. And now, if we replace Ex in this equation, right, then we get these two equations. Jx is equals to sigma naught Ex and Rh is equals to Ey Bz by Jx is equals to 1 by NQC. Now, look at this equation. Q is a fundamental constant, charge of electrons. C is another fundamental constant, speed of light. So thus, what we can do is that we can find out N naught or NO, N observed in Hall experiment, if we can measure RH from the experiment. So NO is equals to 1 by RH Q C. Now, as I said that we can calculate N, the charge carrier density, if we know the crystal structure data. Now, ratio of experimentally measured value NO and the calculated value N. So this ratio NO by N, ideally this should give me a number equal to 1. So if we get NO by N is equals to 1, that will validate the correctness of the Drude model. Let us see what are the values of NO divided by N for different metals. So if you look at the alkali metals like lithium, sodium, potassium, rubidium, the match is very good because the number that we get is very close to 1. If you look at noble metals like copper, silver, gold, then the match is not that good because the numbers are slightly away from 1. Okay, however, now if you look at like divalent and trivalent metals like beryllium, magnesium, aluminium, etc., in that case, the Drude model fails completely because not only the number is far from 1, the sign is also different. You see the minus sign here where we have plus sign over here. Okay, so this implies that if the electrons are charged negatively in these cases, right, in case of monovalent metals, the electrons are charged positively in case of divalent and trivalent metals. But this does not make any sense. Let us test one more thing using Drude model. Before we do that, we have to know one more postulate of the Drude model. Electrons achieve thermal equilibrium only via collisions. After each collision, electrons emerge with a velocity which is randomly directed in accordance with the temperature at the site of the collision. So let us look at the figure and try to understand this statement. So as you see in this diagram, these gray arrows all possible directions in which the electrons can be scattered. And then you see these red arrows and green arrows and blue arrows. These are the actual directions in which the electron is getting scattered. Now you see electrons are still getting scattered in different directions, and the size of the arrow, this is proportional to the speed with which the electron emerges after the collision. So for example, size of these red arrows, which we assume to be at high temperature, these are very large. So that means electrons is emerging with a large velocity after this collision. Whereas the size of the blue arrows, they are very small, which implies that the electrons are emerging with a relatively small velocity after collision from a region which is at low temperature. Let us try to understand thermal conduction in the Drude model. So we know that thermal current is proportional to the temperature gradient. This is the Fourier law. Now let us consider how does thermal energy flow from hotter to the colder region. So let's assume that this region is hotter and this region is cooler. And let's assume some imaginary plane separating the two regions. In these regions, in this is a hotter region, electrons will emerge with higher velocity after each collision. And in this region, which is a cooler region, electrons will emerge with a lower velocity or smaller velocity after every collision. So that means electrons crossing this plane from the hotter region will have more kinetic energy than compared to the electrons crossing from the cooler to the hotter region. As a result, there will be a net flow of thermal energy from the hotter to the cooler region. Now, let us try to estimate thermal conductivity by using this formula. Kappa thermal conductivity is equals to 1/3 CV V square tau, where CV is the heat capacity, V is the speed of electrons, and tau is the relaxation time. Now, we can also estimate electrical conductivity using this formula. Now you see that both these equations contains this term tau, which is difficult to measure. However, we can get rid of this tau if we take the ratio of kappa by sigma. So let us do that. So kappa by sigma is equals to CV V square tau divided by 3 divided by n E square tau divided by m. So we can cancel tau. Okay. And now we use some classical result, that is the internal energy U is equals to 3/2 n kBT, where n is the electron density, kB is the Boltzmann constant, and T is the temperature. And then the heat capacity is the derivative of internal energy, that is del U del T, and that turns out to be this 3/2 n kB. Okay, now we just put CV equal to 3/2 n kB in this equation. So such that we get 3/2 n kB, and we have V square by 3, and we have n E square by m. So then we can cancel n, and this turns out to be kB by E square half m V square. Now we know that half mv square is equals to 3/2 kBT. That is, kinetic energy is related to the temperature in this way. So this implies that we can write kappa by sigma is equals to 3/2 and then kb by E whole square T. And this implies that, calculate this turns out to be like this. So this is known as the Weidmann-Franz law. You see that the number in the right hand side, it just depends on two fundamental constants, kb, the Boltzmann constant, and E, the charge of the electron. So this number is known as the Lorenz number. So that means in an experiment, I would just calculate, or I would just measure the thermal conductivity of the metal. I would just measure the electrical conductivity of metal at some given temperature, and that number should match with this. Okay, now if you calculate this Lorenz number, ideally the Lorenz number from the Drude model, this turns out to be 1.11 into 10⁻⁸ watt ohm per Kelvin square. And now if you calculate kappa and sigma in experiment, then that ratio turns out to be 2.22 into 10⁻⁸. And then if you look at different metals, it varies slightly, but still it is within a range of like 2 to 2.6, correct? So that means the Lorenz number, according to the Drude model, it differs from the experimentally calculated value only by a factor of 2, which is a remarkable success of the Drude model. However, there is a small problem. We can also experimentally calculate the electronic CV, and this turns out to be 1/100 of the classical limit at room temperature, which has been used by Drude. So then there is a question that if the experimentally observed heat capacity is off by a factor of 100, then why the Lorenz number is not off by the same factor? Finally, let us summarize whatever we have learned in this chapter. So both the success and failure of Drude model is mind-boggling. So if we consider Hall effect, then it is very accurate for alkali metals, but it fails very badly for divalent and trivalent metals. Lorenz number, the prediction of Drude model is very close to what is observed experimentally. However, the experimentally observed CV is off by a factor of 100. So in that case, how come the Lorenz number is so accurate if CV is wrong? So in this course, we will try to see what additionally we need to do to overcome these difficulties. But let us try to guess the reason behind the failure. There can be two sources. The first one is classical model. Remember that Drude model starts with Newton's second law of motion and classical limit of heat capacity. So we have to check whether if we apply quantum model, whether we can overcome these difficulties. Next one is free electron approximation. We assume that there is no electron-ion interaction. So this can be another source of error. So before we discuss further, we need to learn the basics of quantum mechanics. Thank you.